So what I want to try to do with my talk is motivate the use of machine learning from a more theoretical, even philosophical perspective. I'll talk about prediction and forecasting, but a lot of the talk will be machine learning as an analytics tool to parse complexity model outputs. And maybe my turn to be a bit provocative, use machine learning as a way to peer inside the black box of physics models. A little note, I'm listed at P&L on the my name tag and all that. I was a postdoc at P&L when we started organizing this workshop a while ago. I had some career turbulence in the recent times, was in industry for a while, but just last week I signed an offer at NERSC at Berkeley Lab. I'll be supporting AI for science. So yeah, get to keep doing some cool work like this. Okay, so to get started, to kind of motivate this idea of physics models as black boxes, I'm going to put my theoretical physics hat on and talk about this idea of this constructionism paradigm, how fundamental physics goes about answering questions, and kind of one of the reasons we don't study climate the way we study fundamental physics. And I'll talk about understanding extreme weather events in that context. Then I'll move to prediction and forecasting, talk about data-driven versus physics-based models, and maybe see that they're more closely related than is perhaps appreciated. And I'll advocate for thinking of, instead of physics-based versus data-driven, kind of explicit versus implicit modeling paradigm. What comes out of this, in particular, these probability distributions over future observations given pasts, that kind of leads to this idea of stochastic models that we've been seeing more lately. And I'll talk about deterministic versus stochastic models in the context of multi-scale systems and some cool stuff there. And then finally, I want to talk a bit about data-driven causal discovery for dynamical systems. Give an overview, some of the theory we developed, some toy model examples, and then some pretty preliminary climate applications. All right, so what am I talking about with all this fundamental science questions? This constructionism paradigm, I'm going to go through an example, kind of set the stage. So it's Rayleigh-Benard convection. If you've never heard of it, before you have fluid in a box, heat it from below. At low temperature gradients, heat is conducted or transported via conduction through the fluid. The fluid is stationary, its velocity is zero everywhere. But at some critical threshold of the temperature gradient, you keep turning it up, all of a sudden heat is transported via convection. And in convection, you have these cool patterns that emerge. Hot water wants to go up, the cold wants to go down. Have to kind of self-organize into these patterns, often like hexagons and maybe some deviations from it, which is cool in itself. But a scientific question is, what in the system determines what that critical gradient threshold is, and how do we go about understanding that? Well, the story of this particular case is quite interesting and very illuminating. So in 1900, Henri Benard does the first controlled experiment studying this, measuring the gradient experimentally. Important thing to note, he does free surface convection. So the top of the fluid is open to air in his experiment. 16 years later, Rayleigh does the first theoretical analysis. So what he does, he has the typical conservation laws, uses these constitutive relations to put the thermodynamics in, and does what we would now call linear stability analysis to say when the conduction state becomes unstable and convection takes over. He gets a number. It doesn't really agree with the experiment of Benard to anywhere near experimental uncertainty. Over decades of more experiments, more calculations, this difference persists. Then in the 50s, some people thought, oh, key thing, in Rayleigh's constitutive relations, he included buoyancy effects, but not surface tension. So he made what we call mechanistic hypothesis, that buoyancy is the driving mechanism of the instability in the system. In the 50s, some people thought, well, maybe it's not buoyancy, but surface tension. So Pearson basically does the same calculation, but in his constitutive relations, neglects buoyancy, adds surface tension. Does a linear stability analysis, now it matches. And this has held up over more experiments and computations, and this is the accepted mechanism for instability in open surface convection. And what Rayleigh was doing was, closed surface. If you do experiments with a closed surface, it matches his calculations. So this is kind of an overview of constructionism. And paraphrasing Feynman, he has in this lecture at Caltech, you can see on this video, says the following: we look for a new law by the following process. First, we guess it. Then compute the consequences of the guess to see what it would imply, and then compare that with the results of computation with experiment or observation. And this has worked well in a lot of cases, but there are some assumptions here that break down for complex systems. In particular, computing consequences and seeing what they would imply. I mean, other things like you can't do experiments in a lot of cases. But this is where we're getting into this idea of complex systems. So for instance, can we take this same approach to understand the mechanisms that give rise to the emergence of extreme weather events like hurricanes or atmospheric rivers? So if we were kind of taking that quite literally, if we'd have to solve the general circulation equations and then find all of the solutions that give rise to the extreme weather events we're interested in. But in particular, in the convection case, it was easy to isolate the different mechanisms of buoyancy versus surface tension. But in something as complicated as climate or the Earth system, it's not always possible to do this. So this paper, very interesting paper by Tim Merlis, he's not talking about extreme weather events, but energy balance in top of atmosphere, feedbacks in top of the atmosphere energy balance. And to study these feedbacks, you can use linear response theory. You can have like a linear decomposition of different components that affect top of the atmosphere energy balance. Last talk of the day. But then if you want to try to attribute how much each of those components contribute to various feedback mechanisms, you do these like so-called locking experiments where essentially you're like testing different mechanistic hypotheses by trying to pull these out. But he shows nicely in this paper that there are nonlinear interactions among these components, so you cannot do unambiguous attribution. And this is like a generic problem that these like mechanisms become untangled, and it's difficult to disentangle them. So for the extreme weather events, like a question we want to know: as the Earth warms, how will storm tracks change or evolve in the warming climate? So we can take a bunch of our climate models, run them forward. They have different parameterizations, different kind of mechanisms in there. Different things will happen in there, but that's kind of black boxy. We can't say exactly how various changes in the particular models lead to exact changes in the behavior of these events. So that's like kind of the black boxy nature in complex systems. We use the term emergence sometimes. So, okay, so we have to do something different. And to do like brute force, like we run these big simulations and we just see what happens to the extreme weather in there. But we have a bunch of data. So what we need to do is have some automated methods to identify the extreme weather events and track them for us to parse this data. So something like a hurricane tracker, like you see here, which was kind of my first forays into scientific machine learning. I created a unsupervised extreme weather tracker here, like you see here, to automatically identify these things in data. So I don't want to go too much in how we do this. Basically, it's a clustering algorithm, but we're clustering over these light cone features that track local interactions in the system. They have some cool properties like some symmetry, space-time equivariance. And when we do this on some climate fields, some of these clusters kind of co-occur with the things we're interested in, like the hurricanes we just saw. So when I was working on this, my motivation at the time was kind of general interest in coherent structures, how we define these things and identify them, because there isn't really ground truth to how do you determine what is a hurricane or what is an atmospheric river. That's kind of an ongoing. Yeah.
It's a quick question on this causal identification. So this is for some kind of finite sound of
Yeah.
So an incompressible fluid that it wouldn't work, I guess, or what would that?
Yeah, what we think you can kind of think of it as like a control parameter that controls for the phenomenon you're interested in. It doesn't strictly have to be like a causal spread, but say like speed of convection or advection in the system that you're interested in. Does that make sense?
So you could do it also for Rayleigh-Bernard.
Yeah. Yeah, it doesn't have to strictly be the causal limits of the system. Because, right, speed of sound, that would blow up too fast. Yeah, so, had general interest in this. We were collaborating with Berkeley Lab. They were interested on a more practical level. Of course, domain scientists have ways of identifying hurricanes and atmospheric rivers with like meteorological heuristics. But the problem they're having is what I was saying. If you want to apply this to these big climate surveys, you want your identification to be uniform across those. But these meteorological heuristics tend to be sensitive to particular model outputs, in particular the spatial resolution they're sensitive to, so it's hard to apply them uniformly. They were hoping for something that was more robust across those. And just some things to point out that you can see in the paper here. Our unsupervised method is indeed more robust, in particular across spatial resolution. And an interesting to point out, so you can see on the top figure, we do find things that seem to, correspond to known structures like hurricanes and atmospheric rivers, but there's a bunch of this other stuff in the tropics. And then you can ask, are those meaningful or just noise? And we did an analysis of extreme precipitation events and found there's statistical significant association with precipitation extremes associated to these things that are not atmospheric rivers or hurricanes by comparing the association with these Tika outputs that identify hurricanes and atmospheric rivers. Yeah.
Say something about what's the underlying principle that you use to identify the red region?
Yeah, so it's using these clusters over light cones and on top of some other things of like hidden symmetries and breaking hidden symmetries, that you get like a uniform cluster on the background, and you kind of anything off of that uniform background is like a broken symmetry that we call coherent structures. Maybe worth a longer discussion.
Maybe you're familiar with Lagrangian coherent structures?
Yeah, we're motivated a lot by Lagrangian coherent structures. And thinking, in fact, of like, for Dimitri's question, like Lagrangian light cones in the context of fluid dynamics. Yeah. Yes?
I'm curious about your causal filter.
Yeah.
So I usually think about causality over time. In this case, you're testing for causality within each grid cell to each other.
Yeah, it's like spatial causality over time. So in particular, these like past light cones, as you go backwards in time, the past light cone is kind of all the spatial grid cells that could have affected the cell you're interested in at that given time. And so, yeah, there's some subtleties here of like in some systems you can be very strict about that. Here we're thinking like this like Lagrangian light cone ideas like following a Lagrangian flow, what Lagrangian trajectories could reach your current target from a given spatial point at a given time. That's kind of this idea behind this light cone. So it's like a weak causal filter of like, I'm only interested in stuff that could have affected my point, and then I'm going to cluster based on that.
So do you mean that you have this blue cell in the middle?
Yep.
And the green in the next slides? These are all cells that could be reached by Lagrangian trajectories
Correct.
initialized in the blue.
Yeah, something like that. Yeah, okay. So kind of back to this point of like, are these structures that, as far as we know, don't have a meteorological known identification, are they something interesting? And there's kind of like a conundrum of using machine learning in this way for this kind of like diagnostic thing. If like you can reproduce something that people already know, like hurricanes and atmospheric rivers, that's cool. People will be like, oh yeah, you did it, that's nice. They'll trust your result. But then like if you could have done it otherwise, you didn't need the machine learning. So you want the machine learning to do something new and interesting, but then because it's black box, people will be like, well, I don't trust it. What is it? So it's kind of a tricky thing. Something cool we did here is we applied this method to this 2D turbulence vortex gas. So you have these vortices that appear, and like-signed vortices repel each other. Opposite signs can merge. Because of this merger, you have a well-behaved decay over the number of vortices over time with an empirical decay rate. We applied our method, counted the number of kind of vortices we identified, and we matched that decay quite well. Whereas if we do k-means directly on the vorticity field without doing these light cone features, just kind of a vorticity thresholding, qualitatively, it's not like it's not on the vortices, but the quantitative match is not as good. So we kind of bolster that we're identifying something physically reasonable here. Okay, gonna switch gears now to prediction and just like modeling. So when I started my postdoc at Los Alamos in 2020, in addition to some other interesting things that were happening in the world at the time, this was around not in weather and climate. I was with a subsurface physics group, but fully data-driven models in certain cases were now starting to outperform kind of standard workhorse physics models. And people in my area were kind of freaking out about this, like, oh, they don't know the physics. What's happening? How are they predicting so well? And I was also, reading some papers from Dimitris's group about these Koopman operators, and thought we could do something kind of interesting here to better understand what's happening. So we're all pretty familiar with this picture at the moment, but kind of set things up. You have the true physical system, you have its state, and the dynamics evolve it forward in time. You have this semi-group property, which is to say the state of the system at a future time is fully determined by the state at any other given time in the past. You don't need more than that. So you have the full state, you can predict forward in time. Of course, in practice, we don't have the full state, and that's one of the whole issues. We have these bunch of measurements. You do inversion, assimilation to create, this approximated data image. But the idea here is like those missing degrees of freedom are at least approximately but explicitly constructed in your data image. So where you didn't have measurements before, you'll have some value there in your data image. And then the physics model evolves that forward in time because, we have some idea of what this physics is going on in the true dynamics. We can approximate it. And that, again, involves kind of explicit interactions among your degrees of freedom that you've had to explicitly approximate to push that forward. To kind of keep the picture simple here, although it's not exactly as we've been talking yesterday, but let's say the data-driven case, we're going to go directly from our observations and just try to learn a function, a map, that pushes that forward to tell you what the observations will be at a future time. So like, the physics model is trying to approximate this thing, this true dynamics. What is this thing trying to approximate? And it's the action of this Koopman operator. Dimitris just introduced it. I like to say, for kind of earth science crowds, I think these like observables that we were talking about are kind of measurement instruments. And the action of the Koopman operator is like a measurement instrument that sees into the future. So it'll tell you what your measurement will be at some later time. And then by the definition of this composition, it's exactly equal to letting your system do its thing and then take your measurement again. And that, gives you your training here for your data-driven model. So you have some loss function like this. Your model is trying to approximate the action of the Koopman operator. There is some unique minimizer, I think Tom mentioned in his talk. This takes the form of a conditional expectation value, which I want you to keep in mind. And so instead of coming from this from the like functional analysis point of view, from my kind of statistical physics background, I wanted to think about this in another way, like where do these forms come from? So you kind of think you have your observation that you see xt, that's a partial observation. I define the set bt here as like the set of all the underlying full system states that are consistent with the observation you've seen. So when you take your observations of all these system states, they'll give you what you've read on your measurement. There's a bunch of them. But again, we know the physics down here. The true physics is the blue, this phi. It evolves forward in time. You get some other set of future states. Apply your observation, all your instruments to those. And those are the sets of future observations that are consistent with your current observation. And again, this set is kind of given by the action of the Koopman operator. Now, that's instantaneous, so just taking one observation, evolving it forward in time in a data-driven way. What about when you take multiple observations, so kind of history-dependent prediction? Well, you have this, start with this set of consistent underlying states. When you evolve forward and you take another measurement, some of those may not be consistent with what you actually see in your data. So like as you take more observations, you kind of constrain the underlying states that are consistent with the sequence of observations that you make. And that improves your predictive power. So as a kind of, and just kind of again, the blue lines here are the physics. You just kind of can't see them, but you see the effect of the physics in your observations and what you're training on. It's kind of a nice demonstration here with a data-driven model of analog forecasting, super old method. In the first upper left here, we're going to do instantaneous but full state prediction of the Lorentz 63 model. So we have our x, y, and z variables. We give it at each given time, give that to our data-driven model, predict the future, and it tracks numerical integration out to about 4 Lyapunov times before they diverge. If we take the same model and just give it x alone, so partial observations instantaneous, it diverges immediately from the numerical integration, but it's still kind of physically consistent with these rotating around the two little wings of the Lorentz attractor. If we stay partially observed, we only have the x variable, but we take past values of it, not just the instantaneous. We again recover predictive skill, matching integration out to 4 Lyapunov times. And this works for other more complicated, like reservoir computing was super popular as a data-driven dynamical system prediction method. It's also history dependent, and you see the same thing there. So the idea here is, there is physics encoded in data-driven models, and then, physics models also obviously have some data-driven component, particularly in data assimilation. But I think it's interesting to think of like implicit versus explicit here, that the physics is given implicitly in data-driven models, and like the history dependence is really important there. Hybrid models can do both explicit and implicit, like neural differential equations will have some explicit component, and you fill in some missing pieces implicitly with the data-driven component. Okay, so if we take this idea, and like, instead of thinking just about the set of underlying system states that's consistent with what we see, like we can put a probability measure on that, kind of push it forward, go through the observation, and talk about now distributions over future observations conditioned on pasts. Kind of why I was interested in this, some of the work my PhD advisor Jim Crutchfield has done for a while is think about optimal models and kind of fully discrete stochastic processes as kind of these equivalence classes of distributions over futures conditioned on past. So I kind of was trained to think about these probability distributions quite a lot, and then I see them pop up here. I thought that was very interesting. And then of course now most people here are familiar with these probabilistic models like GenCast that are, in fact, they are modeling these distributions exactly, conditioned distributions over future states conditioned on past. I think it's pretty cool. I was like really excited when this paper came out. And then like this, I want to talk about multi-scale systems now. The system itself is maybe not that interesting, but a potentially interesting lesson to be seen here. So this multi-scale, and that you have like a slow dynamics driven by a fast noise, and the noise in this case is not actually noise, it's a fast dynamical system here. So the actual system we're going to see is this like quasi-stable. It oscillates around +1, -1 with kind of jumps between. So you have the slow dynamics as this bistable thing, and then it's going to be driven by one of the pieces of the Lorentz attractor at a faster speed, and that driving is what bumps it around from +1, -1. And we're going to look at 3 models just real quick. A hybrid that explicitly models the slow dynamics, but tries to learn that fast driving with a reservoir computer. By the way, I'll call this like the multi-scale signal, multi-scale time series. If we try to learn that multi-scale series directly with just a deterministic model, the reservoir computer, will see what happens, and compare that to learning the same thing with a stochastic, fully data-driven model. So the hybrid thing, like, it works pretty well. Qualitatively, you're getting the jumps. Like, this thing is super chaotic. You don't expect to follow the jumps super well, but just take a bunch of different, one of these, look at ensemble, and you're seeing jumps between +1 and -1. And this is, again, you're using reservoir computers to try to learn the chaotic driving, and you're plugging that into you're assuming the known form of the slow equations and integrating that forward in time. But if you try to just take that multi-scale signal, learn that with your reservoir computer, try to predict, you don't get the jumps anymore. So if it's initialized at one of the quasi-stable +1, it just stays there. And again, think of this deterministic models are learning this, trying to approximate this conditional expectation. So kind of thinking about this as like the jumps are like rare events, and you're kind of averaging them out and missing this behavior. Whereas if you take the same training data, but you train a stochastic model, where you can like actually sample these distributions over the future rather than taking an expectation, you can recover the behavior qualitatively again, where you're actually getting jumps. So again, this system's not that interesting, but it's maybe an interesting lesson of deterministic expectation, conditional expectations versus actually sampling the distributions, and maybe why these stochastic weather models work as well as they do. Don't want to talk about this too much, but if you in multi-scale systems, if you kind of switch the role of fast and slow, you have like the non-autonomous system now with like a slow driving term. You get these tipping points. Tipping points were kind of really big in the news for a while. We were thinking about these data-driven early warning signals. There's some classical statistical signal, like early warning signals for tipping points, but they're not robust. You can have false positive and false negatives. I think the system we were looking at was the ensemble model that you've seen on the poster outside. Another postdoc at PNNL, Pravati Kulov, led this work, looking at some other early warning signals based on some non-equilibrium statistical mechanical ideas, and you can get some more robust signals from there. We're also thinking about some Koopman things in these directions, but didn't get to finish that work, unfortunately. All right, so the last part, most recent work, what I'm quite interested in is data-driven causality. And, again, mentioned kind of this black box nature of physics models. How can we untangle all these like nonlinear interactions? And that's what our interest in causality here is. So if you're not familiar, there is a statistical kind of standard framework of causality pioneered by Pearl. And what does it mean for like Y and Z to be a cause of X in the statistical sense? You have what are called structural causal models, which is to say the values that X takes follow some functional form that depend on Y and Z plus some what's called exogenous noise. But the idea is like, if X can vary in response to variations in Y and Z, then Y and Z are causes of X. And there's, like a kind of small niche community that is thinking about causality in dynamical systems. But interestingly, we were the first, as far as I know, to think about formulating causality kind of rigorously in this way in dynamical systems, kind of less hand-wavy than other things you might see. And in particular, we do this with this flow map idea. Think of it as like taking your model, like a weather model, and evolving it for some given time. So you fix a time t, and you get this map from initial condition to the state at a future time t, and it's just like integrating your model for t times. If we kind of split our dynamical system into some components, you have a cause component and or an effect you're interested in and potential cause. It's this kind of same idea. If this component flow map of one component varies, if you vary another component, then you can say one is the cause of the other. All right. Okay. Let me come back to this. Let's give like an example of this couplered Rossler oscillator. So you have like a Rossler oscillator 1 and 2, and they're coupled together through the y term. So you have this coupling constant C1 and C2. And we have this asymmetric coupled example. We set one of the couplings to 0. So say 2 doesn't depend on 1 at all. So like however you change components up here or values in 1, it's not going to change the dynamics of 2 because there's no dependence there. So that's what all this math is trying to say. Now, it's all well and good to write that out, but in practice, these flow maps are very complicated objects. And in particular, like if you want to say like how much does X affect Y, you can't, there's no real sense of that here. And it's hard to work with in practice. And, coming to this Koopman thing, this trade-off of nonlinearity for linearity in infinite dimensions, it turns out to be a useful trade-off here. So in the paper, we, rigorously derived the kind of Koopman equivalent of this causal definition we came up with. And basically, it's tracking flows in this functional space, and if you hit some of your functions with the Koopman operator, do they pick up dependence, functional dependence, or not? And that's kind of your cause. To work with this in practice, we have this idea of like coming up with a marginal model and a joint model, where the marginal model, say, depends only on X, a joint model is going to depend on X and Y, and does adding that dependence increase your predictive power? And this, if you're familiar with Granger causality, it might sound very similar, and conceptually it is. In dynamical systems, though, I had this whole thing before about how past values carry information about unobserved degrees of freedom, and that actually really messes with Granger causality. If you were to apply Granger causality to dynamical systems, it breaks what's called this separability assumption of Granger causality. So if you ever see Granger causality applied to dynamical systems, be very skeptical. So an important thing of our method is we don't use kind of history-dependent observables. It's all instantaneous because you don't want to conflate these influences through this like delay embedding thing. Okay.
So omega C is it's a space of functions,
Yes.
and omega E is also a space of functions.
Or, okay. It's, sorry. The omegas are not space of functions. They are subsets of phase space. So it's like, so like x1, y1, z1 would be like omega 1, or one of the omegas, x2, y2, z2. And then the full system is the product space of those two.
Okay, but then how does MKT
Yes.
operate on phase space?
So you're operating on the product space, and then it's like, whether to say whether the functions depend on x or not is whether they're constant.
So
over
it
there.
sounds like omega C is a function space, depending.
The functions are functions on omega. It's a phase space. Yeah. Yeah, I guess without getting bogged down too much about this, we have this data-driven measure. For this particularly, this asymmetrically coupled thing, we see that the causal influence, where there is causality, increases over time, roughly linearly, because the equations have a constant coupling, so that's kind of what you'd expect to see. Whereas the direction where there isn't any causality except for a little blip here, we don't detect that, or we detect zero causality as we should. Getting into something slightly less trivial, Lorentz 96 is this asymmetrically coupled nonlinear oscillators. So because of the asymmetric coupling, you have this advection across the oscillator. So if you do like a perturbation experiment where you have two of them, you evolve them over time. The only difference is you perturb like the middle oscillator, and then you take the difference between those. This difference spreads through space over time. So space is horizontal, time increases from top to bottom. You see this difference spreads out over time at a well-defined rate that's following this advection in the model. If you haven't seen this, it's kind of similar to the slinky drop thing. If you have a big slinky, you let go of the top, the bottom kind of doesn't move until it learns that until it finds out that the top has been let go, and it's kind of the causal thing. So like the bottom hasn't moved yet because it kind of doesn't know that the top has been let go. So that's similar to what you're seeing here. So what we do for our causal measure to kind of discover this is we're going to take a single oscillator in the middle, and we're going to ask what are the effects from the other oscillators on our middle oscillator. But we're going to do this kind of cumulatively. So to the values you read here is like in neighbors to the left, how much do they causally affect the central oscillator? So this is like the left 50 neighbors have a given causal effect here. The left 25 neighbors have a given causal effect, and likewise the right neighbors here. And so at a given time, you see it increases up until a plateau. Adding more and more neighbors, you're not getting any more causal effect. When we move time forward, you see that plateau moves over, so you're adding more and more neighbors. You can add more of them and keep seeing causal effect before it plateaus out, and then even further time. So if I kind of scroll through these, you can see this thing moves to the left over time. And in fact, it moves at the same rate that you saw that perturbation spreading experiment. So the kind of causal flow matches this kind of information flow that you see for the perturbation, which is pretty cool. Okay, and then, yeah, some very preliminary results. We came up with this because we are interested in trying to understand feedback mechanisms in climate models. The nonlinearity is really difficult there, so we're thinking about these causal methods as kind of way to come up with this. In particular, one of the things our big collaboration was interested in is like heat transport into the Arctic through the ocean through different mechanisms. So something we see here, looking at changes in Arctic surface temperature as function of different transport pathways there. And one thing to see, the stuff at the top that starts high and decays away are like surface effects or shallow water effects, whereas things that grow slowly over time are more deep water effects. It's not super clean. Some things like NAO has a big bump and then dies off, but it roughly follows kind of intuition we would think there. Another thing, Pierre Gentine's group picked up this work and wrote like a neural network version of doing these like joint and marginal models, and they looked at INSO, and in particular, so what you see in the color here, like the blue stripes are like La Nina events, gold is El Nino. The black line is causal effect measured between sea surface temperature to pressure, and you see that spikes of this causal effect often, not always, but often co-occur with these El Nino events, La Nina, El Nino. Again, preliminary, but kind of interesting. Yeah, so I'll stop there. lot of things going on here, but again, my interest is machine learning as this tool for analyzing and kind of trying to parse complexity in physics models. Again, this kind of, as a kind of counterpoint to what Tapio was saying this morning, that, I'd say physics is not always interpretable. That the word emergence comes up often in complex systems. I think that gets lost sometimes in this discussion of physics versus data-driven, that physics is difficult and the climate is a complex system. Climate models are themselves complex systems. So, yeah. Take questions.